Okay. So it's the last lecture. So today I did the whole cosmology course a little bit backwards because I wanted to bring out the things relevant to gravitational waves earlier, maybe. But thought I'd give you some of the more standard things right at the end. So we'll look a little bit today at structure formation, which is exactly how the structure that we see in the universe, how it forms, what we can say from it, and how we can constrain various properties of the universe using it. But I will. Yesterday, I didn't quite manage to finish talking about the sort of tests we can do with gravitational wave propagation. So I said that that LIGO has tested the dispersion relation of gravitational waves to especially the part to do with the speed of propagation. So that essentially has eliminated all possibility that in the late universe, the sort of physics which would allow you to do some acceleration while at the same time modifying the speed of propagation are allowed. Okay? So these terms may exist, but there's some scale which makes them. But there is, if you remember, I wrote down this action yesterday for the gravity waves, which looked like, so this was the second order action, which looked like the following. There was some overall time coefficient here times the kinetic and the gradient terms for the gravitational wave, and today I'm dropping the indices because it's just. So I'm already setting the sound speed, to the speed of gravitational waves to 1, since that's the constraint is already well established. This part, which we're allowed to have in principle. And if you think about what this is, it's normally what sits over here as a normalization. Remember, this comes from the term in the action which looks like 1/16 pi g times the Ricci scalar, or in other language, m Planck squared. So that's a typical mass scale for gravity, and it's a very, very high scale. Multiplying, it's some constant, it's a fundamental constant of physics, multiplying the whole action of the gravitational wave. But in principle, this is allowed to be a function of time. So given the balance that we have in cosmology, violates this Lorentz invariance, function of time as the overall normalization. So this meaning of this A is essentially is a time varying, let me call it A squared, just to be. This is a time varying Planck mass. So really, deeper down, you should think of this as a space-time varying Planck mass. So you have some sort of field which has some value, and this field gives you the local value of the Planck mass. So it could be different in different places in the universe, in principle. And this has an effect on how the gravitational waves propagate. So if you just try to derive the equation of motion here, you end up, I wrote this down last time, you end up with an equation for the gravitational wave in cosmology. There is from this A comes the Hubble parameter. When I do the derivative, when I do the integration by parts of this term to vary it, but then there's a bit here which looks like plus 2A dot over A. Plus so now in Fourier space K squared H is equal to. The propagation equation looks like this. So in cosmology, there's this 3H part here, which means there's a friction term, and the fact that in a cosmologically expanding background, the amplitude of the gravitational wave decreases. But if you have a term like this, you end up modifying this friction term. Okay, which means that in principle, the gravitational wave will evolve according to will change its amplitude slightly differently than you'd expect from the expansion that you measure using light. So what I said last time, I defined this variable, which is h times the scale factor, and now times a, like that. And that this v, if I plug that into this equation, you find that essentially this v is just an oscillator. So it's a wave that's of a constant amplitude, which tells you that h is going down as, so the solution is, if I rewrite this equation in terms of v, I get a solution which is v is equal to some v0 times e to the I omega t minus k dot x. So I get some oscillating solution at amplitude, and therefore I can say amplitude for h is, and this implies that h is going down as 1 over a. So you get a correction to the amplitude. And what this means is that you get a correction to luminosity distance. Okay? So you know that the cosmological solution of gravitational waves was the standard source term that you had with the chirp mass and frequency and so on, but it was 1 over the luminosity mass and luminosity distance. Luminosity distance comes from this 1 over a. If you do the integration, if you change your variables to redshift and so on, this a will become a luminosity distance. So here what I get is that if I reinterpret this, the luminosity distance for light, so the one I measure just using my standard photons, supernovae, the dual of diameter distance, right? So using the baryon-acoustic oscillations, is in fact not exactly the same as the one I get from gravitational waves in this case, but it's corrected by the value of A at emission and a ratio of the value of A at emission observation. Okay? So in principle, if I have some source in some place where the value of Planck mass is different, so say Planck mass is varying in the universe as a function of time, it's different to the one I measured here today, the luminosity distance I will obtain by doing a Hubble diagram using my gravitational wave sources will be in fact different than the one that I get by mapping this out. So in principle, on one hand, this is in standard general relativity where there isn't such a correction. This is just the measuring the Hubble diagram and gravitational waves should be exactly the same as light. So it gives you a systematic check. But in principle, there's new physics that you might find, this evolving time Planck mass, which might make this different. And the question is, like, to what extent do we know something about Planck mass? I mean, locally we know what it is, but what can we say about what the value of the Planck mass was at some other time in the existence of the universe? Actually, constraints on this are poor. So the only one is the one that actually Ricardo mentioned earlier, about BBN. So when the temperature of the universe was about an MeV, what happened is that the nuclei of neutrons into nuclei to form helium and other light elements. And this process, the neutron has a half-life when it's free, about 7 seconds. So we know we would form a different amounts of helium if the universe were expanding rapidly or much less rapidly compared to that time scale. So in fact, the neutron lifetime gives us a time scale in that early universe. And from this we know that whatever was the expansion rate at the time, so H BBN versus the fiducial one that that we think we have in standard theory, right? That this could not have been different than -1. This cannot be different than about 10% is the maximum. Is the maximum change we can put at this time. And you can interpret this in many ways. One of the ways to put this by saying, look, there were not other relativistic species at the time, because they would have added to the energy density and they would have changed this expansion rate. Another interpretation you can make is essentially that, if the Friedman equation is m Planck, is the density divided by m Planck squared. So if you're saying that h cannot be different than something, that means m Planck cannot be, right? So there's a constraint on m Planck at BBN compared to m Planck on F. This is not very precise. It's of the order of 10%, right? So it has to be, I guess, -1. Has to be less than order 10%. So this is what we know in terms of it's really the strongest constraint we have. Funnily enough, you would think we know how gravitational strength has evolved, but this is really the only one we have. So in principle, this might be something that is this could be a function of time. We have no idea in principle. But so this is right. Then there is a problem of measuring H0, right? Because in principle, this could be running even today, right? So close to redshift 0. In fact, if you think about that, maybe some modification like that might be responsible for acceleration, then it's maybe you would say it's more likely that this will have changed at late times than at some early time. So in fact, so I said, locally, for things that are at redshift that is low, you can expand this integral as being delta z over h0 for some small z. This is h0 in light. And you can do the same thing over here, but you just some perturbation, and you get delta z over h0 GW plus some delta, how do I want to do it? So delta z a dot over h0 a, something like that. Yeah, it's some logarithmic derivative of a that appears here. So, and I guess GW. So there is a difference in the value of h0 that you measure. Okay, so once we get to the stage where if the problem cosmology is not resolved, and there are these two different values of h0, and you go ahead, you make a measurement, and it becomes precise in gravitational waves, and you find that it's a different one, there's another possibility that in fact you're seeing that that h0 is you're actually detecting the fact that the Planck mass is evolving. So if you want, the hard statement is that really the geometry, I was telling you that gravitational waves move on null geodesics of the space. The right of the metric, the hard statement is that gravitational waves move null geodesics of what's called the Einstein frame metric. So you can make a transformation between different metrics. In one, you might have something like this. So the gravitational waves are coupled in some way to some external field that's causing the effective action to be slightly different. Or you can whole what you call your metric, thing where the gravitational action is completely, you can just rescale it. Your gravitational action is standard. This A is just equal to a constant, and you're putting this difference in the matter sector. So matter no longer moves on geodesics of that metric. So there's this kind of dual picture, and so by doing Hubble diagram in gravitational waves, you're really making a Hubble diagram of this Einstein frame, which might be different than what's called the Jordan frame, where it's the frame on which light and matter move on geodesics. So this A, good. Okay, so yeah, well, so anything that is an overall rescaling of well, in the simplest case, something like exactly. So in the simplest case, if I write down a theory which is some phi times r, this is just a renormalization of mass clearly, right? Because Planck mass sits in the action sits here. So but in principle, anything that you multiply curvature by, which is a kind of rescaling, So this doesn't happen in massive gravity. This is purely a so given the things that are still allowed, it's kind of the brand. This is it. But that will change the gravitational wave speed, so you have to tune against that with something else, and then it gets very complicated. There's some tuning you can do to cancel the things you don't want, but but really it's kind of well, okay. So this is a bit out there, but important to bear in mind that in fact. Okay. So saying that, let me change tack. Oh, sorry. Mm-hmm. So what I would say is the following: the Einstein frame is defined in which is a frame defined in such a way that this action is exactly standard. So you have some theory, and write down. You can pick any frame. Right, so you can define them you can pick any fields and combine them to form something. But there's only going to be one frame in which the action is just completely standard for gravitational waves. And that's the Einstein frame. And that frame, you're really just doing cosmography of that frame by doing, this sort of measuring distances by using gravitational waves. But that frame is not a frame in principle in which light and matter, on the geodesics of which light and matter move. So here it's interesting. So this is a conformal rescaling. So null geodesics don't change when you do conformal rescaling. But what changes is if you want the masses. So things that are not conformally invariant. So something like the mass of particles changes if you change. So what remains constant in such rescalings is in fact the ratios of masses, for example. So one way of thinking about it is that if I have in one frame, I'm changing the mass of the Planck mass. If I go to the Einstein frame, what I'm doing is I'm changing the value. So Planck mass is just constant, and I'm changing the value of masses of all the particles. So then if I'm changing masses of the value of particles, so if I have imagine that I have some emission from some hydrogen atom, and there's a particular line that I'm trying to probe, that is determined by the potential of the, by the mass of the electron and the potential of the proton, and therefore, if I change my masses, the frequency of that line changes. So I perceive it down here as being a different redshift or something like that. Yeah. Okay. But whatever happens, however, whatever variables I choose, I must get the same observable, right? So this is the game here. So you pick the ones that are most convenient for you. No. Actually, I'll have something to show eventually. Okay. So any other questions here? Okay. Then let me change tack. So what I would like to talk about is really. So I would like to talk about the fact that the universe is not homogeneous at late times. There are various concentrations of matter which source a gravitational field, and then that causes things like cleansing and so on. So I will talk about such physics. But I would like to start by saying where this all comes from. So I'll be a little bit, I'll sketch this rather than, I don't have the time to talk about this in detail. But roughly what we think, so given that we've observed the CMB and we've able to predict it, our idea roughly is that there's a phase of the universe. So if I write a line like this, so this is the late universe. So this is matter dominated and then acceleration over here. So this is time. I'm going to call this time equality right here, where between when matter was, so matter is dominant over here, radiation is dominant over here. And what we think, and the CMB is imprinted somewhere a little bit later at recombination. And what we think, so we have some radiation-dominated era to some very high energy, but somehow we need to set up this CMB that we observe over here. So what we have learned from this is that the CMB must come from some physical process which roughly has produced a nearly scale-invariant spectrum of perturbations initially, and then they get processed by the evolution from the beginning of the universe to this equality. So there is somewhere in the past, there's some process we're going to call reheating, before which we're in an inflationary phase. And the idea is the following, is that there's an initial phase of the universe, which is it's expanding with W so it's accelerating, and what that means is that H, the Hubble parameter, so I'm plotting H inverse over here, so I'm plotting scales. So this is roughly the size of the causal patch of the universe, is constant. Sorry, this is until reheating when this process ends. Then H begins to, as the universe enters radiation-dominated era, H begins to decrease, and therefore 1 over H increases, and then there is, let's go this way. You go from radiation domination to matter domination, and H decreases but slightly more slowly. Okay, and our idea is that during this phase, modes, so remember things are redshifting, universe is expanding, therefore physical scale lambda for some wavelength is going to decrease as 1 over A. Sorry, it's going to grow as 1 over A. It's going to grow as A. So modes, whatever length scale they happen to be at, initially, let me just draw something that will actually cross. This is a bad color. This one. So they will. So this is a length scale for a mode. So there's some mode lambda 1. Okay, it's a you set up some overdensity of a particular scale and just evolve it. It will, this particular mode will, since it's growing together with the expanding universe, it will. So here it will start, at very small scales locally. It will leave the horizon as lambda becomes of order 1 over H, and eventually, as the universe reheats and H begins to decrease, this mode will re-enter the horizon again. So our idea is that this process of some sort of vacuum at very, very small scales being stretched out across the horizon allows a particular scale to be imprinted in the variance of the fluctuations of this mode. And then when we actually observe the CMB over here, what we're really observing is kind of the initial condition which was imprinted when this mode left the horizon initially. So the statement is roughly that for any canonical quantum field which is in some vacuum state over here, by the time it leaves the horizon, its variance, so this is, I'm just computing a 2-point correlation function. Is determined purely by the value of H when this mode left. Okay, so now if I have a setup, so its variance is essentially of order H squared. So this is the initial condition, right, that we observe over here. And the model we have, so what causes this? It's some accelerated expansion, must end at some point, which h is slowly decreasing during this early time. So there's a very, so actually this is not exactly constant, there's a very slight tilt this way in this 1 over h. So actually modes leave with slightly different amplitudes. This is the, and we've measured this, and we've managed to measure this difference. So this happens for any field, really, any light field during that time. So in particular, it happens for the, so yesterday I had this action for a scalar perturbation and for the gravitational wave. So it happens for both of them, except the scalar guy is not, in fact, canonical. So what you end up with is that the variance of the curvature perturbation is h squared k, just make sure I don't, times epsilon, where epsilon I'm defining as the difference, so I'm defining this h dot over h squared. So it's the rate at which this is evolving. Whereas the gravitational waves also get this spectrum. I think Mario told you this yesterday. But they don't get corrected by this epsilon. So there's a natural hierarchy between these two that depends exactly on the model and the early universe. Okay, but the idea here is that essentially inflation imprints for all the light fields a very universal power spectrum, correlation function. And then, I remember I showed you this I derived this equation during radiation domination, but there's something like this valid during the whole history of the universe. The zeta is conserved whenever zeta is just constant. So whatever gets imprinted over here, until it again crosses the horizon, this is a constant quantity. So, and you get other modes, which I drew this a little bit too. This should have been a little. But in principle, you get other modes which leave at later times or early times, depending on the scale. So, what we really have is a theory for initial conditions. This is inflation dynamics. We've measured the amplitude of this correlation function. So actually, let me write down something. So there is a dimensionless version of this guy. Which is just multiplied by k cubed, that thing. Measured this amplitude of the order of 10 minus 10, depending on how you define your pi's. This changes, but so this is really something that we've measured by looking at the amplitude of fluctuations in the CMB. Okay, and we've measured that it's nearly scale invariant. It varies very slightly, to the extent that you know that this thing is some power of k, which is minus 0.04. Okay, so it's nearly flat. And the gravitational waves we have, which tells you there's some issue with the setup a little bit. Yes? What matters is the value of so there is this. So this h that you have here has M Planck inside it. So it's driven by some density of an M Planck inside it. And so in the Einstein frame, where gravitational waves are completely standard, and this is just the result, is the Einstein frame h that is here. But M Planck in principle might be a varying function of time, and in fact, it's somehow in this h dot over h squared. There's a derivative of this M Planck sitting in there. exactly. So you find, in fact, that epsilon can be very, very big. You can sort of, sorry, I mean, 1 over epsilon can be very large, which essentially means you're enhancing the scalar fluctuations much more than so, and this is exactly, so this is in this, in these models like Higgs inflation. Right, okay, you think the Higgs is the inflaton, roughly. You're adding to the standard inflation action some term, which looks roughly like this Higgs. So there's some parameter psi Higgs times R. Yeah. So this is a normally coupled model. This is the inflaton, so it rolls, and therefore the effective Planck mass is changing during this time. So it's very different than what we. So this is the reason why essentially the gravitational waves are suppressed in these models, and they completely evade the constraints that we have right now. Because you're right. So in the standard case, essentially we should have already seen them, because if you take m squared phi squared inflation, all these things are very simple, and you should just have seen. Yeah. Exactly. Exactly. Yeah. Yeah. So. Exactly. Yes. Yeah. So H is the Planck. This is the. So H today is something very small, and in these models, it's in the past, it's some large value of a field, and therefore Planck mass, since it's equal to 1 plus this, is higher. So gravity is weaker. Okay, so how much time do I have? Okay, so maybe. So what I'm now interested in, though, is that we've measured the CMB, and essentially this gives us a picture of what the initial conditions were over here. But if you even want to be ignorant about this, and so it gives you initial conditions for the universe over here that you've definitely measured, and now you would like to understand what the universe might look like today, right? So over here is radiation dominated, but as you cross this line, radiation goes away very rapidly, and what you're left with is essentially baryons, and you're dominated by dark matter. Okay, so over here it's mostly dark matter that's around. So if you want to understand the structure of what's happening in the universe and the distribution of matter, you really have to understand what dark matter is doing. So let me just tell you that you can, just looking at the conservation equations for the edge momentum tensor for dust, you can show that dark matter will be, let's say, delta m. It grows as the scale factor out here. So provided that you're outside of the horizon, it grows as the scale factor out here. During radiation domination, once it crosses, remember I showed you that the potential was constant, super horizon, but once you enter the sound horizon of the radiation, the potential begins to decay as tau minus 3. So that's essentially stops this growth. And during radiation domination, if dark matter enters if it enters the horizon, so sub-horizon dark matter, so for the mode which was here, which entered the horizon over here, inside here it stops growing. So there's some weak growth like the log of the conformal time, or log of the scale factor. But essentially this growth disappears once the mode enters the horizon. It gets suppressed because the radiation oscillates and the pressure stops the growth of the potential. And the radiation dominates gravity here, so essentially dark matter is kind of just a small contribution. But after radiation ends, and there's no more pressure in the universe, so you're just dealing with non-relativistic stuff, you also lose the scale. So there's a scale of the horizon, but you lose the scale of the pressure, and therefore actually the horizon doesn't do anything anymore. And what this means is that after matter radiation equality, this delta just grows as A at all scales. So people define, let's say, astrophysicists studying the late universe define the growth function, which is essentially the exact function that this delta takes as it goes from here, from beginning of matter domination to today. So it grows as A until acceleration era, where this growth begins to decay and it slows down. But there is no scale anymore. So really what that means is that there is in principle, a feature in this, so this part of it, because there's no scale at all, so you just, all the perturbations grow at the same rate, right? They all grow as A, all the way down here. But before there is some sort of feature that appears, because those which entered the horizon already before equality, they will end up being suppressed compared to those modes which were outside the horizon during this time. And this ends up leading to the shape of the matter-power spectrum. Okay. So here was the dimensionless power spectrum for the initial conditions. So you just start with a uniform one, roughly. So there's a small tilt, but it's nearly uniform. This gets imprinted in your density perturbations and in all the fields that are around in the universe, radiation domination. But once radiation is gone and you're trying to understand what's out there in the universe, you end up with, so people instead plot traditionally P of K. So the difference between the delta and P of K is K cubed. So I had this already here, right? There's a difference between, let me define it for a second. So this thing looks like, let me draw it first. And so this is K. This is the mode K. So this is scale 1 over lambda. Okay. So you end up with functional dependence like that. Now, this P of K is the correlation delta delta. It's dimensionful, so you get this dimensionless one by multiplying by K cubed, but people use this one. And delta delta, if you think about your so in Newtonian gravity, or this thing is actually K to the 4 times the potential, the Newtonian potential, right? So you have Gauss law if you want. Nabla squared phi is equal to delta. So there are two of these nablas, so it's in Fourier space, it's K to the 4. So what I'm plotting is the matter power spectrum. I'm sorry, I was supposed to use orange, and I swapped. It has this particular shape, and essentially what this replicates what I was telling you, which is that at scales which, so this particular scale over here is the scale of equality. So it's the scale at which the mode kx entered the horizon at time tx. Okay? And this is actually modes which had shorter wavelengths before that time and entered earlier. They end up being relatively suppressed because everything is growing as A for the longer modes, but these guys, in fact, right? Well, they remain, log t, whereas everything else is growing as whereas on this side, you have exactly modes which never entered the horizon when radiation was around, and therefore phi is constant. So phi is constant. There's a constant power spectrum initially. This is the same as the spectrum in phi. This P of K is 1 over K cubed of this. So there's a K to the 4 over here divided by K cubed. You get this proportional to K behavior. Okay, so really what this means is there's a scale invariant spectrum up to here, and then there's a very sharp suppression. So, and then this is imprinted at equality, and then it just evolves. It just scales as some function of the scale factor. So A during matter domination, and then that growth slows down, but it's just rescaled, but the shape is fixed. So this is the lambda CDM prediction for this. So we would like to measure it. So how do you go about it? Well, you try to find it in the sky and do it. The problem is that this is made of this is the matter. You can't see it. But what you see is galaxies. So you say, well, okay, I'll measure my power spectrum of galaxies, and I will replicate. Wait, do I have to? Let's skip that for the moment. So you've seen this. So okay, this, like I said, so I've seen this before, right? So what this object is correlation function. It's just a transform of this. That you see here is exactly the wiggles over here, same. And so this is just a Fourier transform, and you can even see, look, they've shown this is the correlation function of galaxies, not of dark matter, and shown the lambda CDM gives you exactly the correct prediction. But it's not quite right, in that the statistics of galaxies are not the same as the statistics of dark matter. The reason for this is this, that in principle, the dark matter field, delta, in real space looks something like this. Okay. So some places there are peaks, some places there's less density, there's not more density. Okay. You're only forming halos, so the structure, so the dark matter collapses and eventually forms a blob of dark matter, we call a halo, in places where this peak was sufficiently high. So there's some threshold. And let's say there's a lot of debate or really how to define halos when they happen, etc. It's model dependent, etc. But in principle, there's a threshold above which you ensure that you form a halo. And only when you form this halo do you find that there is, in fact, the baryons inside it can form galaxies. So there are galaxies, but only at these peaks. So if I try to do the power spectrum, if I try to find the power spectrum of the correlation function of the dark matter, by looking at the correlation function of galaxies, which is really what I've measured over there, there is a bias between the two. It's only sometimes in very particular places in the dark matter distribution that I will find a galaxy. So I'm only looking at distribution of these very special points inside the dark matter. So in fact, people write down some bias parameter like this. And this is, in principle, unknowable. So I don't know what this is. So the argument is that this should be roughly, since we're dealing with linear physics at sufficient scales, it should be roughly constant. But you can only really measure it by comparing what you can really see, which is the galaxies, with the thing that you think that you have, which is the dark matter power spectrum. Okay, so there's this problem that there's this bias parameter. It was not understood that this is the case until the early 90s, which means that if someone tells you they've measured the bias, that means they've basically measured inside the lambda CDM. So there are reasons why, I mean, there are bias models, right? So you can, of course, do some fit infer it in some Bayesian sense, but it's not observable. So let's say the sharpest prediction of cosmology would have been the exact shape of this power spectrum in dark matter, but we can't see it. So what can we do to see it? Let me say one more thing. So let me define a so you can see that these peaks have some amplitude, right? And I'm telling you that the amplitude of this power spectrum grows as A, which means that there is some sort of number, which roughly, is maybe, which is related to the amplitude of this power spectrum, which is something that we can use to discuss, really how this looks like in the late universe. So, people studying the CMB always talk about amplitude in terms of the initial perturbations. People working in late universe really want to talk about this, which is the derived parameter inside the model, right? So you start with this, and eventually you will get to the amplitude over here inside some model. So you might want to try to measure this particular parameter, this amplitude. So you can define a parameter called sigma 8. Actually, let me define sigma r. So sigma r is the variance or the distribution of mass taken in spheres of r megaparsecs in size. And this is, they have dk by k, k cubed p of k. It's related to the amplitude of this power spectrum, but you need to apply some window function, which is to do with how you're going to average. So it's sigma squared is linearly proportional to the amplitude of p of k, or sigma is proportional, p of k is delta squared, so somehow morally it's proportional to delta. So this parameter, in fact, exactly r equal to 8 megaparsecs. It's called sigma 8, and this is what people in the late universe measure to try to ascertain what this might look like. Okay? So that's a definition. Blah blah blah. Okay, so now let me, in the last half hour, tell you what you can do. So first thing is, essentially, since I cannot see this, I would like to do some measurement which will somehow be a function of what this power spectrum is. So one thing we've been talking about all the time is these luminosity distances, angular diameter distances. So I would like to maybe somehow try to use them to ascertain what is happening over here. So remember, okay, let me write down. So I wrote this before already. The universe at late times is not homogeneous and isotropic. It is slightly perturbed. You can see what the size of these perturbations is. It's of the order 10 to the minus 10 square root of, so 10 to the minus 5. So these, and there are scalar fluctuations. Sorry, it's a minus. So these two scalar potentials inside the metric, which are sourced by matter. So I wrote this down before. Okay, so the metric looks like this. It's not exactly FRW, but it's slightly perturbed. There are these two scalar potentials phi and psi. And remember, I wrote down, when I was discussing distances, I wrote down this equation for the Jacobi map, for how the it's some sort of it's something that came out of the geodesic deviation equation for a bundle of photons which are starting somewhere and then moving out to the observer. So it tells you about. So I wrote this down in the first lecture. So it tells you. So there's an equation you can derive for this, which is fully covariant and independent of the space-time that I've defined, which tells you about how angles evolve, or which defines the distance essentially. And when we were doing this in FRW, this term was 0, but you can of course redo this calculation in a perturbed space-time. And what you find out is that this Jacobi map, which defined what the angular diameter distance was, remember? Let's see how I want to write it like that. Gets corrected. Okay? There's a bit which is, so this guy is the angular diameter distance. There's a bit which corrects, so it's a matrix, so this is just a delta function in FRW. So delta function times the angular diameter distance. But this gets corrected, so there's a trace part, if you want, which corrects the angular diameter distance. And then there is a matrix, which is a matrix of shears. Let me say. So actually, I've just parameterized an arbitrary, so this is a 2x2 matrix, and I just parameterized it by some arbitrary properties. So it needs to be, sorry, this is a minus gamma 1. So it's trace-free because the trace is over here. This trace is called the convergence. And these gammas are called the shear. Now, in principle, there's also, so this is completely, I'm doing completely arbitrary decomposition. In principle, there's this omega over here, which represents rotation. But in fact, this only appears at second order in these phi's and psi's. So you don't see it at linear order. But at first order, you get some convergence, which is a correction to your angular diameter distance. And you get some shear, which is in fact some warping of the shape of this Jacobi map, which tells you how the shape of the image maps onto the screen. Let me call this Aij. So Aij, you can show, is some integral over some kernel. It's called a lensing kernel, from the source to the observer. So times these potentials, sum of these potentials. So if there's a non-zero potential, light will get warped, and it gets warped. So you can rewrite in some basis, gamma 1, gamma 2, you can rewrite this object. It gets warped by some second derivative, some Laplacian of this potential. And there's a similar expression for the convergence. So the point being, if I take some object, like a galaxy, which is an extended object, it has a shape, and then I just let the light shine toward me, the shape that arrives is going to be slightly different than what I have. So this is the standard picture, right? That you have galaxies, they have some shapes, and they arrive and they have slightly different shapes. And actually, and sort of in terms of comparison, this is some simulation that I found. So roughly some blobs, they look like this. The actual field processed, this is enhanced by many orders of magnitude, right? But roughly, you end up getting slightly different shapes. So by looking at the shapes of galaxies in some statistical way, because galaxies are not circular, but if you look at shapes of galaxies, you can extract some integral across this potential. And this integral tells you something about the amplitude of this power spectrum. So we've been doing this, and so you can see there's the sigma 8 that I was talking about, and omega matter, so there's some degeneracy between these two parameters. We've been doing this since, I guess about 2013 was the first time there's any cosmological signal seen, but that's not plotted over here. And you can see that now so this is the same story as H0. There's a value for Planck, which is very, very tight. And that's essentially the value you get by looking at the CMB and projecting it forward, assuming lambda CDM. And then you're making measurements of the late universe using lensing. And then there are special cameras which look at very wide patch sky. They're very precise in terms of that they don't warp the shapes of these galaxies, so you don't introduce systematics. And they roughly measure value for sigma 8, which is compatible with Planck. So this is, let's say, DS, which is right now our best, most precise measure that we have. But let me just this agrees with what Planck sees. So there's nothing to. So the amplitude seems to be as expected. But there is another collaboration which is doing something similar with a slightly weaker instrument, and so this is a publication from a year before this. So it's slightly different Planck results, but you can see there's some slight tension. So roughly historically, there's been a tension over here, which is actually quite significant, and it's been reducing as time has gone on. And But as far as I understand, between these two collaborations, there's still no agreement about who's right. So these are claiming that that this tension exists. So there's been this sort of story of being maybe not quite enough power. So you can maybe roughly see that the sigma 8 is a little bit lower, the average, than what you expect from measuring the CMB. I mean, a story like that. But it's may or may not be going away, but this is something that's really, this is a measurement that we're doing cosmology as time, DS is running, and they'll be publishing some new data today soon. So, 20 minutes. Okay, so that's one thing you can do, and then there's another thing you can do, which allows you. So remember, how would what there's something called redshift space distortions. Sorry, let me just say one more thing. So remember, this equation is valid for gravitational waves, right? It's just exactly the same. It's the same metric. They're both propagating, and the same null geodesics of this metric, right? So gravitational waves, in principle, are seeing exactly the same sort of effect, right? This part is irrelevant because you're dealing with point sources essentially. So that's it's not quite point sources, of course, but in reality, you never resolve the size of the orbit. So this part you will never see. However, you see, in principle, you might see exactly this bit. So you might see that the angular diameter distance, or the luminosity distance in the case of gravitational waves, gets corrected by some factor. So what this does, it seems if you take some event, if you have positive convergence, so there's some appropriately arranged lenses between you and the source, you find that the angular diameter distance that you read off is in fact slightly shifted. The object's magnified. So if you don't know about this, you might interpret your observation as being much closer than in fact is. And there's also even a shift in redshift. So there's a sort of you're changing both the redshift and the luminosity distance a little bit. And for things that are close by, it's completely irrelevant because the amount of mass that you have to integrate over is very small from the source to you. But if you look at something that lies at cosmological redshifts, so this is more futuristic, but you might in fact begin to get affected by this. So this will introduce some bias into your data. Okay, but let me just do this. There's another thing that, and so okay, if I plot the correlation function. So again, this is just the Fourier transform of this guy. I'm taking galaxies. Pairs, I'm looking at some separation, I'm looking at this excess probability of there being there, and this gives me this zeta. I defined this a few lectures ago. Well, okay, this is that, and I'm telling you the amplitude of this is sort of unknown because it's determined by this bias, right? So you see the amplitude for the galaxy correlation function. You don't know the amplitude of the thing that you care about, which is the dark matter correlation function. But there is an effect which has now been measured, which occurs. So you expect this thing to be homogeneous and isotropic because the universe is homogeneous isotropic. You expect this correlation function to only depend on the scalar value of the separation, but not to the orientation. Or so just really, you expect this to be the same everywhere in the universe, and you don't expect it to be dependent on the angle. But turns out that if you take this data, so this is exactly the same data, but you plot it in 2 dimensions rather than 1, where you look at the separations between galaxies, and you plot here the correlations with respect to the line of sight. So I'm looking over here. If the galaxies are, what's the word? If they're really parallel to my line of sight, I put them, on one axis, and if they're perpendicular to the line of sight, I put them on the other. When you do that, you can see that roughly is the same thing, right? So there is this peak in the middle. That's the same peak as that one. There's a little bump over here from the BAOs where you can sort of see. But you can see that over here in the middle, this is not a circle, which you'd expect if this were isotropic. And the reason for this is that when you have scalar perturbations in the universe, if there's an overdensity, things around there are more likely to be flowing toward this overdensity. Right? This is what scalar perturbations really mean, that it's not rotational motion, it's sort of to do with divergence. So really it flows in and out. So what this means, therefore, is that you are more. So remember, you're looking at correlations. So it's not that there's some peculiar velocity which some particular galaxy has. It has nothing to do with any of the others. So you're looking at so the ones that are sort of interactions between galaxies, the existence of some particular overdensities, and the fact that they're bound into some sort of system. So what you find is that the galaxies which are along the line of sight, they're floating if they're kind of, imagine that, is there a pointer? Yeah, so this is the center of the overdensity. And now there's a galaxy over here. You're trying to work out there's some separation for these galaxies, and you're trying to put it at some particular redshift. What happens is that there's a cosmological expansion which is causing this thing to have some particular redshift, but then this thing is more likely moving away from you because it's floating toward this overdensity. So when you're looking at things that are separated along your line of sight, you actually find that things tend to cluster around the redshift of the central object. Whereas if they're floating parallel, there's a perpendicular line of sight, then you don't see this correction. And this induces a quadrupole in the power spectrum, in the correlation function, and the power spectrum too. So the size of the squashing effect tells you about the velocity of the galaxies. So now the velocity of the galaxies is roughly given to you by the velocity of the potential that accelerates them. Sorry, by the gradient of the potential. So the acceleration of the galaxies is the gradient of the potential, so the velocity is some integral of this quantity. But it's related to the depth of this potential psi, this Newtonian potential, which is in the 0, part of the metric. And we've measured this velocity, right? So there's some. So to do this, you have to. So for lensing, what you need to do is build the camera, which firstly has a wide field of view, because you're doing cosmology, so you need to see as much as you can. But the shape of the objects you're measuring must be extremely precise. But you don't care so much about the redshift, because the redshift is just you bin it to some large redshift bins, and you don't really care so much about this. To do this, you have to get the redshift extremely precisely. Completely different experiment. You have to put, a spectrograph on every galaxy, to determine exactly the redshift, or you might introduce some systematic error. So completely different surveys are doing this sort of studies compared to the weak lensing one. So you can see that this is the case. And roughly, the errors on this are very big. So there's a big problem, which is that this effect becomes nonlinear and hard to predict at scales which are at scales which are exactly the scales on which you want to measure it, right? So it's like it's more nonlinear than the matter spectrum. So I've done this prediction linearly, this is nowhere near good enough, and then you have to somehow figure out. That's a hard thing. Actually, this is the reason why the errors are so very big on this, because the systematics are kind of. But there's been this trend again for a long time. You can see that all the central values, apart from this one, and the ones over there, lie on one side of this line. So there's a kind of hint, if you want, that somehow the galaxy proximity velocities are sort of lower than you might expect them to be. That the potentials that are being driven by this dark matter are somehow not quite as large, or maybe that this value of this sigma is different than the amplitude of the power spectrum is less than you might expect. So this is essentially the two measurements, which are very complicated, and I haven't even bothered telling you about the problems to do with nonlinearities in here. And this is really a very simplistic view of what's being done. But they're kind of showing that there might be something different than the standard lambda CDM prediction. So, if you want the next decade in cosmology is really this. So, we put this here because I sort of thought we're about maybe 20 years ahead of the gravitational wave community, right? So we had our first detections of the CMB and so on measurements really somewhere around the year 2000. And the strength, the precision of our surveys and the size of our surveys have been increasing ever since, right? So we are kind of at the stage where we have roughly put the model of cosmology together, and it seems to work very well. But we're getting down to precision level, percent level precision, and you're beginning to discover that they're here and there. So, but of course, things are planned out all the way down to the 2030s to continue making these measurements. So this is a Euclid plot from a long time ago, but you can see that roughly we are here. So 2 surveys. This one is finished, and this one is taking data right now, and they've only had the first release of the first data. And there'll be a 3-year and a 5-year release. So this is for weak lensing. But the next stage is, supposed to start 2020, 2021. There's a very large telescope, the LSST, which is supposed to be able to scan its half of the sky very rapidly in rapid cadence and with extremely high precision of the mirror, so that you should be able to extract the shape of galaxies in a very precise sense. So, and similarly, there's a space-based mission that Europe is putting up. It was supposed to be next year, but I think it's 22 now, maybe, not 21. Called Euclid, which is really things. It's a weak lensing survey for the whole sky. So it's an order of magnitude in signal to noise, and things like this, at least on the side of observations, some uncertainty should go away, and problem really is in modeling right now, actually. And then for the other type of experiment, this is this is for the BAO distance ladder, but I was telling you about the galaxy surveys with which you can do measurements of redshift space distortions. Ones that basically have completed their surveys is BOSS. So these are the plots I was showing you, so in blue over here. But the next one is it's called DESI. It's a follow-up, which will. So this is the version where they're going to have 14,000 fibers. So that the way this business works is that you have you roughly have a plate. You make holes where the galaxies are. You put a fiber optic. Then you take it down to a prism, and you look at the spectrum of the galaxy to exactly pin it down. So this will be able to do. So BOSS was able to do about 1,000 at a time, and this guy will be able to do about 14,000 at a time. So we'll be able to cover much more sky and measure these they'll be able to measure the redshift of the galaxies, of many more galaxies than we have so far. So this should, so really within the next 5 years or something, there should really be some definitive answers, and things will either get resolved on this side or we'll never know. And then to finish off on the side, so this is roughly scaled as a, so this is the CMB, it's at redshift 1100, but most of the volume of the universe is in fact close by. So this is scaled by the actual volume of the universe. So in principle, we cannot see anything beyond the CMB sphere, but we need to map. What we're doing is we're mapping everything inside that, right? And right now we're kind of, so DES is the one that's working. There's this slice over here, and we have the ones in white is really what this BOSS survey has done. So really, this is kind of what the maps that we have right now, and with missions such as Euclid, we essentially be able to see all the galaxies that there are to see, and what's visible. So the reason why that is, so our galaxy lies over here, so you can't see very much this way. So it's kind of limited to looking out in that direction. And you can see the slide is somewhat aged because DES is still there, futuristic 2012, but I haven't seen an updated version. But we're on track to have data to be able to say things with 0.1% precision, and if the tensions remain, then presumably that's a sign that something is different in physics than of the late universe than we expect. Okay, so it's still exciting, despite the fact that this is now an established field with great data and a model that works. It's sort of, there are things that are maybe creeping underneath. So watch this space. So I think I end here. Any questions?